Hello friends, in this video we will continue with our discussion of the Engineering Service Examination 2009 Electrical Engineering Paper 1. In this video we will be discussing questions from question number 16. The previous questions have been discussed in the previous videos. Now moving on to question number 16. This is a question from the control system topic. In this question they have asked us unity feedback system with open loop transfer function of 20 divided by s plus 5 is excited by a unit step input. How much time will be required for the response to settle within 2% of the final desired value? Now, in order to find the solution to this question, first we just write down what are the given data. So they have given us the open loop transfer function that has been written over here, and that we denote it as g of s, and it has also been mentioned that the control system is of unity feedback type. The input is a unit step input. A unit step input is represented by u of t, and they want us to determine the settling time, and the band that defines the settling time has been defined as being given as plus or minus 2%. Now moving on to the solution. Now over here we have drawn the block diagram of this control system. As you can see over here, this is a unity feedback control system. There is no gain in the feedback loop, and in the forward path what we have is the transfer function that is given, and that is g of s. And if we were to write the transfer function between the output and the input, that has been written over here, and that is nothing but g of s divided by 1 plus g of s into h of s. That is the standard formula for the transfer function between output and input in a system having a single feedback. Now if we were to substitute for this g of s and h of s in this formula, we can do that, and here we have substituted for g of s, and h of s is nothing but unity, and we arrive at this transfer function, that is 20 divided by s square plus 5s plus 20. Now if we were to consider the standard form of a second order transfer function, it is nothing but omega n square divided by s square plus 2 delta omega n s plus omega n square. There is also a s term over here. Now if we were to compare this transfer function with this, we will be able to make out that 2 delta omega n is equal to 5. If we were to compare the coefficient of s over here and over here in the denominator, we get 2 delta omega n as 5, and from that we can find out that delta omega n is 5 divided by 2. Now settling time for the 2% band is defined as 4 divided by delta omega n, and in this we substitute the value of delta omega n that has been obtained from here, and we arrive at the value of 1.6 seconds. And if we were to analyze the options, we would find that the correct option is option B. Here we'll have a look at the question. Yes, we have over here 1.6 seconds, and that is the option B, which is the correct answer. We will now move on to the 17th question. The 17th question is, consider the following statements. First, the amplifier gain and phase shift. Second, filter transfer functions. Third, two-port network parameters. Fourth, power gain in a two-port circuit. Which of the above quantities can be measured using a vector voltmeter? That is the question. Now to find the solution, we will just see the options that are given. We have been given 4 options, and if we were to see what is a vector voltmeter, it's a special kind of voltmeter that measures both the magnitude and phase angle of the voltage. A normal voltmeter would measure only the magnitude, but in this case we will get the phase angle also. Now, in order to measure the first parameter, amplifier gain and phase shift, the vector voltmeter can be connected at the input and output of the amplifier, and the gain and phase shift can be determined. Now this process is quite straightforward. Now if we were to connect the vector voltmeter at the input and output of the filter, and if we were to sweep the input frequency through a particular range, we will get the gain and phase shift for different frequencies. Now if we were to get this, we can find the Bode plot, and using asymptotic approximation we can find the transfer function of the filter. So using vector voltmeter we can get the second option also. Now if the vector voltmeter is connected at the 2 ports of a 2-port network, we can do the network analysis by appropriate open circuit and short circuit methods, and we will be able to find the various 2-port network parameters. So the third option is also correct. The first 2 are already correct, as we have already seen. Now the fourth option is power gain in a 2-port circuit. Now this cannot be measured using a vector voltmeter, so that one would be not applicable. And if we were to see the options, 1, 2 and 3 are correct. Now we'll just see 1, 2 and 3 corresponds to option C, and option C is the correct answer. Now let us see the 18th question. In the 18th question they have given us a circuit consisting of voltage sources in series with various types of impedances, and we have 3 sources of such kinds, and in the question they have asked us to replace the above shown circuit by a single voltage source in series with an impedance. Now to solve this question, we first consider the circuit itself. This is the circuit. We have different sources, 3 different sources and different source impedances, and they want us to find the equivalent voltage source and source impedance. Now the method we will be predominantly using in solving this question is the voltage source to current source conversion, and reverse also. Now if we were to convert these voltage sources into current sources, we get what is shown over here. For the first source we have the voltage as 1 angle 0 and the source impedance as 1 ohm, so we get a current source of 1 angle 0 amperes, and the source impedance would be the same, but the only difference being that it will be connected in parallel with the current source. Now the second source, the voltage is 1 angle 90 volts and the source impedance is 1J. Now the current in such a case would be 1 angle 0, and that current has been shown over here. The arrow mark is missing over here, it should be present. Now the source impedance is 1 angle J in parallel to this current source. Now the third source is 1 angle minus 90 volts divided by minus J, that is 1 angle 0 amperes, and that current has been shown over here, and the source impedance is minus J, which has been connected in parallel with the third source. Now we have 3 current sources and 3 impedances connected in parallel. Now we find the equivalent current source by adding up all these 3 current sources, that is nothing but 3 angle 0 amperes. Now that is what has been shown over here. Now to find the equivalent impedance, we do the parallel combination of these 3 impedances, 1 ohm parallel to J parallel to minus J, which is nothing but 1 ohm. So this is the equivalent current source in parallel with the equivalent source impedance. Now the next method that we will be employing is current source to voltage source transformation. So in order to do that, we convert this current source into voltage source by multiplying this current source 3 angle 0 amperes into 1 ohm, and we get 3 angle 0 volts as the equivalent voltage source. The 1 ohm resistor would not change in value, but it would come in series with this voltage source. So this is the answer that we wish to obtain, and this is 3 angle 0, and the resistance is, or the impedance is 1 ohm. And if we were to see the options, we have an option 3 volt and 1 ohm, so the option C is the correct one. We will now move on to the 19th question. Barium titanium crystal has a thickness of 2 mm. Its voltage sensitivity is 12 into 10 to the power minus 3 voltmeter per Newton. It is subject to a pressure of 0.5 meganewton per meter square. What is the voltage generated? They have given us 4 options. To solve this question, let us first see the given data. They have given us the case of a barium titanium crystal, which is a piezoelectric material, and they have given us the thickness 2 mm, the voltage sensitivity, that is 12 into 10 to the power minus 3 voltmeter per Newton, and they have given us the pressure that is applied, which is 0.5 meganewton per meter square, and we have to determine the voltage that is generated. Now if we were to see the property of piezoelectric materials, the charge that is produced inside a piezoelectric crystal is equal to the charge sensitivity multiplied by the force. The charge sensitivity would be in coulombs per Newton, force would be in Newton. And to find out the voltage, we can divide the charge by the capacitance, and so the voltage generated in the piezoelectric crystal would be the charge sensitivity into force into 1 divided by C, which is the capacitance of the crystal. Now the capacitance of the crystal can be expressed as epsilon A, and at the T at the numerator. Now the area A is the nothing but the area of the crystal sides, and T is the thickness. Now this force divided by area constitute the quantity called as pressure, and so can be represented by P, and the charge sensitivity divided by the epsilon can be represented as the voltage sensitivity. So the voltage generated in a piezoelectric crystal is equal to the voltage sensitivity multiplied by thickness into the pressure. Now we can all these 3 values have been given in this question. We just need to substitute these values, the charge sensitivity, which is the substituted over here, thickness over here and pressure over here, and we get the voltage generated as 12 volts. Now we'll just see the options. The option D is there, which gives the answer as 12 volts. So this is the correct option. Now we'll move on to the 20th question. In the 20th question, they have given us a circuit and they have asked us for the circuit as shown above, if E is equal to E1 and I is removed, then V is equal to 5 volts. If V is equal to 0 and I is equal to 1 amperes, then V is equal to 5 volts. For E equal to E1 and I replaced by a resistor of 5 ohms, what is the value of V in volts? Now E is over here, V over here, and I is over here. Let us now analyze the circuit. Now this is the circuit that has been given. It has been redrawn over here. Now we'll just see the three cases. For E equal to E1, I equal to 0, then V is equal to 5 volt, V is marked over here. For E equal to 0, I equal to 1 amperes, then V is again equal to 5 volts. If V is equal to E1, I replaced by a resistance of 5 ohm, then what is the voltage? Now this question concerns the application of Thevenin's theorem. Now what is Thevenin's theorem? Thevenin's theorem states that in a linear two-terminal circuit having energy sources, it can be replaced by a voltage source in series with a resistance. The value of the voltage source would be nothing but the open circuit voltage between the two terminals, and the resistance, series resistance, would be nothing but the resistance, equivalent resistance between the two terminals with all the energy sources set to 0. Now if we were to consider Thevenin's theorem as applied to this circuit, and if we were to see the point from here to the left hand side of this current source and replace it with the Thevenin voltage source and Thevenin resistance, and now analyze it considering the two cases that have been given. The first case being E is equal to E1 and I is equal to 0, then V is equal to 5 volt. This is nothing but the open circuit condition since I is equal to 0. So with V equal to 5 volt, it means that the Thevenin voltage is also equal to 5 volt. If we study this circuit carefully, we will be able to come to this conclusion. Now the second case is when E is equal to 0, that means that the Thevenin voltage is equal to 0 and the current is equal to 1 amperes, the voltage is 5 volts. Now such a situation would arise in case we are determining the Thevenin equivalent resistance, since the only energy source has been set to 0. So the Thevenin resistance, if we set this VTH to 0, the Thevenin resistance would be the only element that would be remaining in this circuit. So the Thevenin resistance would be nothing but the voltage divided by the current. Voltage is 5 volt and the current is 1 ampere, so it would be 5 ohms. Now we have got both the parameters of this Thevenin equivalent circuit. Now we can substitute them over here. I have redrawn it over here, and the current source has been replaced by a 5 ohm resistor as has been asked in the question. Now we can find out the voltage across this 5 ohm resistor through the voltage division rule. The 5 volt into 5 divided by 5 plus 5, and the voltage V is obtained as 2.5 volts. So the answer 2.5 volts, we'll just check in the options. Yes, we have in the option B, we have 2.5 volts, and this is the correct option. Now let us see the 21st question. In the 21st question, the impulse response of a second order underdamped system started from rest is given by C of t is equal to 2.5 into e to the power minus 6t sine 8t for t greater than or equal to 0. What are the natural frequency and the damping factor of the system respectively? They have given us 4 options. Now let us try to solve this problem. Now the given data is the impulse response of the system for t greater than or equal to 0, and they have asked us the natural frequency and the damping ratio. Now if we were to see the impulse response of a standard second order system and the closed form equation representing that, it is given over here. That is C of t is equal to omega n into e to the power minus delta into omega n t divided by root of 1 minus delta square sine omega dt. Now omega n is the natural frequency, d omega d is the damped natural frequency. Now if we were to compare this standard response in the closed form and the standard response given over here, we will be able to make out that the delta omega n is equal to 6. We can see over here the exponential, and omega d, which is nothing but omega n into root of 1 minus delta square, is equal to 8. We can see it from here. If we see the sine term, we can make this out. Now if we take the root mean square of these two parameters, delta omega n and omega d, we get the natural frequency, which is nothing but root of 6 square plus 8 square, which is equal to 10 radians per second. This is the natural frequency. Now delta omega n, we have already found it is equal to 6, and we can substitute the value of delta omega n here to find out the damping ratio as equal to 0.6. So our net answer is omega n is equal to 10 radians per second and the damping ratio is equal to 0.6. Omega n is nothing but the natural frequency. Now let us see the options. So this option A shows the natural frequency as 10 and the damping ratio as 0.6. So option A is the correct option. We will now see the 22nd question. What will be the type of the system if the steady state performance of control system yields a non-zero finite value of the velocity error constant? They have given us 4 options: type 0, 1, 2 and 3. Let us now see the solution. The given data is that the velocity error constant Kv is a non-zero finite value, which means that it is between 0 and infinity, and they have asked us about the type of the system. Now the type of a system is defined as the number of poles at the origin of the system. Now let us consider a simple unity feedback control system. Over here R of s is the input, C of s is the output, and we have the forward path transfer function G of s and the error, which is E of s. Since this is a unity feedback control system, the gain in the feedback path is unity. Now from this figure we can make out that the error E of s is equal to R of s minus E of s into G of s. Now from this we can come to this, which means that E of s is equal to 1 plus g of s equal to r of s. Now from this we come to this third step, which states that E of s is equal to r of s into 1 divided by 1 plus g of s. Now we can find out the steady state error. That means the E of t as t tends to infinity, E of infinity, using the final value theorem. Now that is equal to the steady state error is equal to limit s tends to 0 s into E of s. This is nothing but the application of final value theorem. Now over here we can substitute the value of E of s, which we have already obtained, and we get limit s tends to 0 s into r of s divided by 1 plus g of s. Now for a unit ramp input, the Laplace transform is r of s equal to 1 divided by s square. Now let us substitute this in the equation for steady state error. So the steady state error is obtained as limit s tends to 0 s into 1 divided by s square, which is nothing but r of s divided by 1 plus g of s. Now we can further do some simplifications, and we come to this step, and finally when we substitute s equal to 0 over here, we get the final form of this equation, which is nothing but limit s tends to 0 1 divided by s into g of s. Now this limit s tends to 0 s into g of s can be defined as the velocity error constant, and with such a definition we come to the conclusion that the steady state is nothing but the reciprocal of the velocity error constant. Now this constant is defined for a particular input, which is nothing but the unit ramp input, and now we'll consider different types of systems and the velocity error constant in all such cases. Now if we consider a type 0 system, it has no poles at the origin. So if we were to consider, let us consider this g of s as p of s. P of s is nothing but a transfer function with no poles at the origin, and in such a case the velocity error constant would be limit s tends to 0 s into p of s, and since there are no poles at the origin, we'll find that this kv velocity error constant is equal to 0. Now for a type 1 system, this g of s can be represented as p of s divided by s. So this g of s has a pole at the origin, a single pole at the origin. So the velocity error constant in such a case would be limit s tends to 0 s into p of s, which is not divided by s, and this would be a constant value and can be represented as kv itself. Now let us consider the type 2 system, and here g of s would be p of s divided by s square, 2 poles at the origin, and kv can be represented as limit s tends to 0 p of s into s divided by s square. Now if we apply this limit over here, we'll find out that the velocity error constant is infinity. Now for a type 0 system, velocity error constant is 0, type 2 it is infinity, and for a type 1 it takes a finite value between 0 and infinity. So since they have already specified in this question that the velocity error constant is between 0 and infinity, we come to the conclusion that the particular system is a type 1 system with a single pole at the origin, and the correct option would be the option B. Let us just check the question. Yes, type 1 is given as option B, and this is the correct option. Next we will see the 23rd question. On which of the following factors does hysteresis laws not depend? Magnetic field intensity, frequency of the field, volume of the material, Néel temperature. Now let us see the details of hysteresis laws. Now Over here we have written the equation for the hysteresis loss per unit volume of a material. It is given as eta n into Bm raised to 1.6 into F. Now this eta n is nothing but the Steinmann's coefficient for the material, and Bm is the maximum flux density and F is the frequency. Now if we were to see the options given in the question, the option A is the magnetic field intensity. So we can see the magnetic field intensity is nothing but H, and B and H are related as B equal to mu into H. So this magnetic field intensity has an influence on the hysteresis loss through the maximum flux density. So this is correct. Now the next option is frequency. Now frequency has an influence, that is straightforward from this equation. Now the third option is volume of the material. Now the hysteresis loss as expressed by this formula is per unit volume. So the volume of the material has a bearing on the net hysteresis loss. Now the fourth option given is the Néel temperature. Now in this equation, Néel temperature is not a factor, so hence Néel temperature has no influence on the hysteresis loss in a material. Now let us just look what is this Néel temperature. Now this Néel temperature is the temperature above which an anti-ferromagnetic material shows paramagnetic behavior. Now so this is the explanation for Néel temperature, and we will just see the question once more. So they have asked us on which all factors the hysteresis loss does not depend. So it does not depend on Néel temperature. The option D is the correct answer. We will now see the 24th question. A strain gauge having a resistance of 500 ohm and a gauge factor of 3 is bonded on a member of structure undergoing tensile stress. If the change in resistance of the gauge is accurately measured as 1.5 ohm, what is the value of strain suffered by the member? Now they have given us 4 options. Let us try to solve this question. Now first let us see the given data. We are considering the case of a strain gauge. The gauge factor has been given as 3. The resistance has been given as 500 ohm. The original resistance, the change in resistance has been given as 1.5 ohm. Now we are required to determine the strain in this question. Now in order to solve this, we need to write down the expression for gauge factor, which is nothing but the per unit change in resistance divided by the strain. Strain is nothing but the per unit change in length. Now from this formula we will be able to come to this: delta R divided by R into 1 divided by gauge factor is equal to the strain. Now we can substitute the values for delta R as 1.5, R as 500 and the gauge factor as 3 and come to the answer that strain is equal to 0.001. Now let us see the options. Now the option B gives the answer as 0.001. So the option B is the correct answer.